Yep.
Yeah.
Okay. Okay, cool. Then let's get going. Yeah, I will be talking about RT-2. We had a couple more projects in the meanwhile. We can mention them later, but yeah, I will focus on RT-2 and we will just go through the kind of motivation and things that made it work and kind of what we're excited about in this project. And yeah, first thing that I have to say is that it's a large team effort. Basically, a lot of people contributed to the research side, infrastructure side, data collection side, hardware operation side, so all kind of things. So I would like to thank them and yeah, mention that this is a lot of people that make it happen. Yeah, so recently, I guess we all saw that the large models have started to change the world. We see them being applied in all kind of areas and also in not only in research, in industry and everywhere. So we have large language models, and more recently, we also saw some success with vision language models, where we have we can query models both with visual kind of concepts and visual questions and language questions. And especially visual language models seem to be very useful for applications like robotics, as we usually have to deal a lot with visual understanding of the world and camera images. At the same time, the language capabilities are important for basically communicating with the robot to convey tasks and to reason about planning and what to do next. Robotics in general has been traditionally difficult for applying basically large models and generally scaling up the learning compared to other fields. A couple reasons for that. Some of like one of them is that the real world data collection is generally more difficult to scale than collection in internet or in places where you don't have to execute things in the real world. We did see that human demonstration is an effective way to collect data, but at the same time, it is a bottleneck as we can only collect so many demonstrations that we have teleoperators and generally without like a large effort to like get more people to collect the data, it still remains a bottleneck. Although it does seem that we can scale it up to some extent by just employing more operators or like pulling from different operators, but it remains a bottleneck compared to other fields. So one I guess one solution for bottleneck in human demonstrations could be autonomous collection, which was, I think, still considered kind of a holy grail of data collection for robotics. But it looks like we're still struggling with collecting autonomous data effectively, and especially getting good quality autonomous data. And yeah, the main reason for that basically is that to get good autonomous data, you have to have already a good bootstrapping data set or something that already brings your policy to a state where it can collect a good, basically can execute things in the real world to a certain degree to get the autonomous collection going. And that bootstrapping part is still, I think, is not completely figured out. So it seems like human demonstrations could help there, but I think for many things we're still struggling. And one thing that can also help with bootstrapping in general and like scaling up data is, of course, sim-to-real. And it is promising. I think at the moment we still not at the level of the like diversity of the real world in simulations. It is improving. We are getting more realistic simulations of more and more scenarios. But yeah, it's just easier to set up a real world scene and just collect some data than to work on like a complex simulation to simulate that scene. So it could be that we will um, get more and more diverse and realistic simulations in the future, but still I feel like it's does not solve the issue. So the question that we have been asking ourselves as we kind of as a team focus on um, scalable robot learning is that given these recent advances in these large models and given that they encode so much knowledge about the world, how can we transfer that knowledge into robotics to kind of mitigate a lot of the data collection issues that we have in the real world? And uh, basically looking into that, we had several milestones over the last couple years. The first work where we really started to basically look into large models and specifically large language models has been the work on SeiKan. Um, there we basically used the large language model as a planner, which would break down a long horizon task into its components, into single tasks, and then we would use a combination of a language model and a Q function trained with Q-learning to get um, skills that are both meaningful and executable in the real world. So the Q function has been used as an affordance model, and by combining scores from LLM and Q values, we would basically go towards grounded planning, where we would plan skills according to the combined score. In this work, we still used a quite small compared to to the today's standards model for the policy that actually executes the actions. And at some point, after adding more and more tasks and kind of language instructions that we train that model on, we started noticing that it becomes a bottleneck and doesn't really scale with increased amount of tasks. So in our next work, which we then called RT-1 or Robotics Transformer 1, uh, we basically worked on scaling up the actual policy, and we switched to transformer architectures which scale well and can handle sequence data. And by doing so, we basically could learn many more like single tasks within the same model. RT1 was still compatible with SeiKan, so we could still use SeiKan as a planner, and then basically RT1 model as a policy. In the meanwhile, there was another branch of works which sprouted kind of from the vision language models. So at first they were not directly connected to robotics, but then we had a project called Palmi, where we took a language model Palm, combined it with vision, and also trained it on both basically web visual question answering and kind of question answering about the embodied scenarios. So and it looked like the model itself was actually getting good at answering questions about the physical world, and also given that it's now had visual inputs compared to the models that we use in SeiKan. Here we notice that the visual inputs help us with better planning, and generally Palm um, has been significantly better, like visual language planner than the ones that we used in LLM. But still in Palmi, we haven't, we still had a separate, we would need a separate policy to actually run things on the robot. So Palmi could break down the task and kind of give us a plan. and do it better than LLM, but we would still need a policy that would actually output actions that are executable on a robot. And that brought us at some point to an idea that given that we already use transformers for policies, and these models of transformers, it seems like it would make sense to actually try and unify them within a single model. And that was basically the idea behind RT-2. So basically take a large web scale visual language model and directly use it as a robot policy. By doing so, we now actually, as I will tell later, we saw quite a bit of generalization to things that are not present in the robotics data, which kind of was surprising and very encouraging. And we also saw new capabilities which were basically not possible before, like things like chain of thought reasoning with combined action execution, and generally all the things that we imagine a language model can do now combined with action inference, basically within the same model. Yeah, so this kind of is our like short overview of our journey regarding large models for robots. And with this, I think let's dive into RT-2 and kind of get to know more details about it. Are there any questions so far? Okay, then let's continue. Yeah, so let's first kind of take a general look at VLMs. So VLM is basically a model that takes in an image and the language kind of query and outputs an answer in a language form. In this work, we tried two different VLMs, and the one that has become our main VLM here is called Pali, which basically consists of transformer layers for language and visual transformers for visual input. Now, as I mentioned, VLMs encompass both visual and semantic understanding of the world. And yeah, in robotics, we do have to deal a lot with both of these. So yeah, the question is how do we leverage all of this knowledge in robotics? So here you see the architecture of RT1 actually, just to compare it to RT2 and okay. Yeah, so for RT1 and yeah, as you see, basically the inputs, main components of it are kind of similar to Pali. So we have language as an input, camera, like history of camera images as an input, and now action as an output. And for RT1, we actually used discretized representation of actions as it is important for basically training transformers efficiently, and which is very similar to a VLM, which outputs language tokens. So as the architectures are basically from the kind of outside are basically the same, just with different token space, we can try to use the large pre-trained VLM directly as a policy. And the main question then remains, how do we actually deal with actions when using these pre-trained VLMs? So here you see our representation of actions for our robot. So we have basically changes in the grip, in the end effector position and orientation. We have a command for opening, closing the gripper, and the command for terminating or continuing executing a task. Yeah. So each of each of these dimensions is discretized into 256 discrete bins, and basically we usually train these models with a classification cross entropy loss similar to any classification model. Now in VLMs, the outputs are basically strings of text. So the kind of most naive thing of representing actions for VLMs is just converting them to a string of numbers. There are a couple of options there. So the kind of most simple and kind of the option that we actually used at the end is to just take token numbers, the same that we used, let's say in RT-1 for discretization, and just put them into a string and use them directly as a target for training. There are a couple of alternatives. We can think of directly using floating numbers, basically without discretization. It's also possible, but like internally, like a language model, basically a tokenizer used in the language model would still tokenize them, and that would usually result in more tokens per number, as like it would use separate tokens for basically for the first numbers and for the decimal point, and for the digits after the decimal point. And with integers, as we use here with token numbers, it's basically usually just using a single token per number, so it's quite an efficient representation. A lot of these models have things like extra IDs. So for example, if you have like a language tokenizer which has like 200,000 tokens, usually like the last, let's say 100 tokens are not assigned to anything. For example, Pali and Palmi has such tokens. So it is possible to use these extra IDs basically for these actions. But this kind of limits a bit the range of basically tokens we can use, because usually you have like 100 extra IDs, which means you have to rediscretize your action to 100 bins, which might be limiting if you want to keep it, let's say, at 256, or a high number of bins. And like one last option that actually also works quite well is to just pick the least used language tokens. So a lot of language tokenizers actually rank the tokens by the usage, right? So, and usually the last tokens are the ones that are the rarest ones. So that's the ones that actually are least used on the internet, and you can then basically reassign them to your action tokens, and in this way avoid the collision with a lot of other language outputs. And yeah, of course, there's always it could be an idea, why don't we just use some kind of human language description, like move left, move right, move top, down. But the problem here is that although it is closer to the original kind of language space, what models are trained on, you cannot directly execute this kind of things on the robot, right? You would need still to convert them to actual numbers that you would send to actual commands that you would send to the robot.
Yevgen, can I ask a quick question?
Yeah, go ahead.
I guess this was more about the robot actions here, but you're using delta change in position from where the gripper currently is.
Yeah, exactly.
So, did you try like absolute position, and or like how does the robot know where the gripper is if it's like out of view of the camera for the robot?
I see. Yeah, but the position is, I mean, it's just from the forward kinematics. So like it's a position with respect to the base of the robot. So right, we can compute it by just using the model of the robot itself. So the links, the length of the links, and
Okay, so you're computing the position for the gripper and giving that as state input, and then your action space here is a change from where the hand was in the last
I see.
state.
Actually, like we noticed that still works well without having the current robot state in the input. So basically, the model only gets image as an input. It was the same for RT1, but the displacement that it outputs is relative basically. But it doesn't get the current position of the end effector.
Okay, thanks.
Yeah.
Related question on the action space, Yevgen.
Mhm.
If I remember this correctly, correct me if I'm wrong, but I think RT1 was also moving the base, right? It had the displacement of the base in the action space.
Yeah,
Or
yeah,
so I'm just wondering here, yeah, how you move the base from.
yeah. So even in RT1, so in RT1, the actual policy was mostly moving the arm and the planning, like kind of the combined planning and policy would then move the base and then the arm.
Okay.
But in general, we do have data where we also command the base pose, but we still don't have like too much of it. So most of the data we used from RT1 is actually just moving the arm. That's why I think in this work we kind of concentrated on just on the arm control. But we did try to train these policies with base. So basically, then our action space would get three more numbers for the base displacement. I think three more numbers. Yeah. And it also works. It's just we just didn't have a lot of data with like significant base moves. That's why it was a bit too early to train on it. But it's definitely what we are kind of working on at the moment as we get more and more data with base displacement.
So thanks.
Mhm. Yeah. So basically, at the end, we went with for Pali especially, we went with the option of directly converting token numbers to strings, as it was like an efficient way to do it, using as like underlying language tokenizer would only use a single token per number. And it was also an easier one and it's one that easy comparable to like to RT1 and other baselines where we used the same tokenization. So now basically by switching to training these VLMs on basically action representation, we start talking about vision language action models, which now basically get vision language as input and output actions. So as I mentioned, we tried two models. One is Pali, for which we had 5 billion and 55 billion parameter versions, and then Palmi from our previous work, for which we had like 12 billion parameters in a model. And our training procedure actually consisted of training on both the robot action data and the internet scale data. And as I will show later, it's actually turned out to be important to retaining good performance, because when we first tried, we actually tried to just fine tune on robot action data, but then noticed that at some point it starts forgetting the knowledge it had from pre-training. And the problem here is that these actions, when you train on them, they constitute quite a large departure from the original kind of language answering dataset, which means we actually have to use higher learning rates and train for longer, which means that we actually forgetting a lot of things a lot of knowledge that was obtained during pre-training. And the way to keep that knowledge is we found out is to mix in some of the pre-training data into the fine-tuning data. So that kind of ensures that you kind of retain that knowledge and adjust your representation to now be able to output actions. We still upweight the robot action data quite a bit compared to the web data. So it still like accentuates the policy training, but yeah, we still keep some of the web data around to avoid catastrophic forgetting. And yeah, we call this process co-fine-tune, meaning that we co-fine-tune or co-train on robot and web data. So as I mentioned, pre-training was done with web data, visual question answering, and the robot data. For the robot data, we just took the same data as we used in RT1, which made it easily comparable. And that data was collected on multiple robots over many months, and has about 130,000 demonstrations. We didn't use any autonomous data here, so purely human demonstrations, and which basically means that we just did basically pure behavioral cloning on this data. Now for inference, excuse me.
Yeah, sorry, I just had a quick question about this. So when you say like the input for the robot action, like when you say that it's just pure behavioral cloning, I'm trying to understand. So that means that like does that mean that there's like the input is always this same query which is like some kind of like relatively high level task, but then your labels in this case are this sequence of outputs? I'm not sure I'm making sense, but like what I want to know is like what like the input output here, like you need the text query to also be part of the input, but then you also need the visual input to be part of the input, and then you need the output to become the like so it's conditioned on all of those things. Do I sort of have that right?
Yeah, exactly. So for a given episode, the natural language instruction, which kind of describes the task, is kept fixed, right? So and then so the language instructions kept fixed, and then the camera image changes, and the action output changes, but the language instruction per episode, per task is fixed.
Okay, got it. Thanks.
Yeah, internally, of course, when it is processed inside the VLM, the like language instruction in some sense is a sequence of words, right, or like of tokens. So like from that perspective, it is a sequence, but then it is fixed throughout the sequence of time steps of the task, right?
Yeah, but so like the interesting thing is like, so over an entire sequence of the execution of this task, the specification of the task remains fixed.
Yeah.
But it's the actual image that you're seeing, which is combined with the specification of the task, which is being used to produce the specific output at that specific like time step. Okay, yeah, got it.
That changes exactly. Maybe exactly to reiterate here. So we have basically our query usually looks like this. So we have kind of a question: what should the robot do to? And then we insert the task name, and then we say A, and then the model has to basically to continue answering this question. And then that goes into LLM, and then the visual part goes into VAT visual transformer. And the output is then like a sequence of basically of tokens, which is then detokenized and sent to the robot. So we run these policies in a closed loop manner, right? So we basically get a new image every time and like rerun the policy to get the updated estimate of the action, which means that actually this procedure is quite costly, especially given that we use multi-billion parameter models. And that's why I have a small cloud kind of picture here. So we to run these models, we deploy them basically in a cloud service where we have a lot of resources, and then we query the model over the network. we are able to run these models by doing so. We're able to run them like up to 3 hertz at the moment, which is of course for robotic purposes, like for general robotics, seems kind of little, like too small amount, like basically too slow. And yeah, we do realize it, and that's what we are currently actively working on. Basically, how the ways to speed it up, to kind of maybe put some parts of the model on device, or like generally speed up the inference. For the tasks we considered in this work, like 2-3 hertz was enough. So it's mostly like picking up things, moving things close to each other, kind of bringing things together, opening some drawers, or cabinets. So for those things, like this frequency is enough. But yeah, if you want to do like dynamic things, or like very kind of fine-grained manipulation, we would need to switch to high frequency. But yeah, these are very large models, and it's active area of research how to make them faster. But like, I guess at the trade-off of the speed at the moment, we do get a lot of generalization. So that's kind of what was also the focus of the work. Okay, so yeah, that was, I think, kind of overview of how it works. In general case, so let's maybe take a quick look at the things it can do. And the interesting piece, I think, in this work is also how we evaluate it. So and this kind of represents a somewhat a departure from the ways we usually evaluate robotic policies, where we like know what we trained on, and we just define a test set, train set, and kind of know what the model could do like in advance in some sense, right? In this case, because like we pre-trained on like this vast amount of data, it was actually not clear what the model would do after the training. So to kind of find out what the model can do, we actually uh, a procedure which we called like fishing. So we would like just get the robot and then start trying all kinds of things that comes into mind, and kind of fish basically for things that can do, kind of try to find the boundaries. So we would start with things we like know it should do, like things that are in distribution, and then slightly kind of try to push out of it. And the kind of biggest axes that we tried are usually along the object generalization and motion generalization. And specifically for this model, we noticed that the object generalization worked really well, and the motion generalization less so, which are kind of maybe intuitive, because we did have like in our initial RT-1 dataset, we had large diversity of objects already. So it was kind of a good point to start scaling it up. Where on motion diversity side, we only had like 5 skills. So I think it's too early to kind of generalize on those axes. We would need more skills on the robot to kind of scale it up by adding basically this pre-training. But yeah, basically on the object generalization part, I think it worked great. I think we were very surprised actually. So here you see some examples of things which were actually not in the training set of the robot data, right? So all these objects like animals, I don't know, like flags, letters, right? So suddenly the model started doing like letter recognition and actually move the arm based on that, recognizing like photos and logos and things like this. And yeah, important to say here, it's not only like recognizing them, but also being able to control the arm to manipulate these objects and kind of move towards them, reason about them in a physical space, basically. We, after doing this kind of several rounds of this like fishing and kind of looking for things it can do, we roughly found like several categories that we thought are meaningful for kind of doing evaluations here. So things like understanding symbols, reasoning about the environment, recognizing humans. And here we saw that, yeah, RT2 with underlying VLMs was like could beat the baselines such as RT1 and also things like VC1, which used a general visual pretraining without language pretraining. So it seems like pretraining on both visual and language parts is important and like brings basically things together which are important for robotics. Yeah, here basically just some visual videos of the same of saying the same things, just to get a feeling what it looks like. Yeah, this kind of maybe slower kind of movements of the robot is due to the low frequency of the execution, but as I mentioned, it is enough to basically accomplish these tasks. We also did some more like quantitative categorized evals where we categorize things into different aspects of what's basically new, what's unseen in the data. So things like unseen objects, backgrounds, environments, and yeah, important thing to note here is that on scene tasks, so actually things that are in distribution, for the robot data, we could match the RT1 performance, so there's no regression there. So that's actually usually a good sign. So we can safely move on without a regression. And then yeah, on the generalization and kind of unseen things and unseen commands, we could greatly outperform RT1 and also other pipeline other approaches which use some kind of pre-training. Yeah, and here, as I mentioned, some numbers for the difference between fine-tuning and co-fine-tuning. So here we see that, yeah, on average, basically, the co-fine-tuned models get us like a boost of 10-20% in performance over the models which are fine-tuned. So even though basically the data is kind of diluted, right, with non-robotics data during the co-fine-tuning, we get more generalization because we retain a lot of the knowledge from pre-training. We also kind of tried it on a completely separate task and a robot. And the interesting part is that actually this was tried separately and then we kind of united, but then we still arrived at the same conclusion, which kind of confirms that these VLMs actually work for this robotic tasks. So here again, a 3 billion version of Pali has been used for the open source language table task, and the data for this task only had cubes, basically these cube objects, blocks basically, and after pre-training and fine-tuning, it actually could operate on all kinds of stuff and basically understand these kitchen objects without ever seeing them on the dataset. And yeah, as the last, we also tried some initial experiments on chain of thought, which is kind of also an inspiration for bringing everything together within a single model. And the idea here was that now, instead of just having a single skill and outputting action, we would first basically train the model to conditioned on a higher level command, like a long horizon skill or long horizon prompt, and then train it to first output the low level task that it thinks it has to perform at this moment, and then conditioned on that basically output action. So it means that this model basically both plans these single steps, and then given then that plan, it can output like the actual action that has to be executed at this moment. And this basically goes towards like completely unifying everything within a single model. It's actually super exciting, I think, because yeah, it just brings this reasoning and kind of action inference together, and also ties closer to the underlying language understanding, because predicting this plan, it's kind of goes closer to the pre-training actually than like predicting action. So we can leverage even more there and then basically add the action on top of it. And yeah, we had some nice results here where like it actually would like, reason about picking up something to hammer a nail, and like reason that it needs a rock and then like pick up a rock. That's that could be useful for like hammering a nail.
Do you mind if I ask a quick question, like about the data sets in this case? Because on the last slide, you're also mentioning that, it's sort of extrapolating to unseen data. But this is unseen data in terms of the robotic interaction data. But it is probably seen data inside of like the PalmE model of the vision text data. So can you talk a bit more about like the difference between those two data sets and like how much data you think?
Here basically for this chain of thought, we basically just generated some of these high level instructions kind of for the existing data already. So like we just took the existing data and generated some high level instructions for the underlying skills, and then kind of just trained the model to predict, not to predict just numbers, but predict basically both the plan and the current action at the same time. So that's the difference. So the data itself is kind of the same. It's just the labeling is different. So you for this data set, we kind of generated these high level commands in addition to these low level commands that we already had. And for the previous experiments, or like for our main experiments, we just basically used this piece, right? We only used the low level command and and output in action.
Okay.
Yeah.
I guess one of my questions is then, well, do you think to improve this type of model, we need more vision language data or more interaction data?
Yeah. So definitely more interaction data. Maybe I will actually go through it in the conclusions and like for the future work. So definitely we need more motion diversity, and like one of the biggest takeaways for us also was that the like visual diversity or like understanding the objects themselves, this almost comes for free with the pre-training. Like it really understands like a lot of concepts and like a lot of like things that it sees, but the motion diversity, that's the piece basically that we have to work on. So like our kind of recipe for making it do more or like scaling it up is actually to collect more motion more motion diverse data, maybe less visually diverse data, but more like motion diverse data, because that seems that's the piece it's actually missing, which also makes us, it means that we are like it's actually what roboticists are good at, or like to do, right? So do like motions, not to collect all kinds of objects. So that's why I think it like puts us in a kind of a good position of like doing interesting things, and also means that we like not out of work. So we like we like still, it's very robotics oriented data collection, where you try to get as much dexterous and as much motion diverse data. Does it answer your question?
Yeah, thank you.
So basically, to conclude, to summarize, we introduced these visual language action models by changing the output of visual language models to output actions. We saw a lot of improved generalization to new tasks, new objects. We saw some initial results for chain of thought reasoning within a single model. And that generally puts us in a good position, because we are kind of riding the wave of the models that are developed by like a large field. So it means that like improved underlying models can actually mean improved robot behaviors and improved robot control. So it's a good place to be, I think, at the moment, because it's just much like it's large community working on it, and we are like kind of getting the benefits of all the recent developments. Yeah, the future, of course, the first thing I think we are looking into is increasing motion diversity, getting more dexterous manipulation tasks, basically increasing frequency of manipulation. Those are basically things that are needed. And yeah, we hope that the visual diversity we will mostly cover through pre-training. Visual and semantic diversity in some sense. We plan to extend on chain of thought capabilities, basically see how we can further combine high and low level skills within the same model. We didn't forget about RL. Actually, recently we had a paper on Q transformers. So basically, training these transformer architectures with Q learning, and all the tricks we found useful to do that. So I also encourage you to look into that paper. And yeah, we do look at the moment how we can take that Q learning algorithm and bring it to VLA, to VLMs, and kind of try to scale it up. Of course, there are other RL algorithms like RLHF and more like on policy like algorithms, which are also could also be used. So yeah, some people look into that as well. Of course, there are many more roads from here on kind of working with these models, and I feel like it's an exciting time actually. Like it's not often that we get generalization like I wouldn't say for free, but like just happening in robotics. Usually it involves a lot of like effort and data collection. So it was nice to see that in this work we basically just use the same data we had already and could get more things out of it. I think that's kind of what's kind of a bit of a relief in terms of what it takes basically to generalize in robotics. I would like to again to thank all the people who worked on it, and I think we could like, if it's okay, we can like continue the discussion. I still have like a half an hour time.
Yeah, of course.
Yeah.
Yeah, thanks for the great talk. I saw that you guys released RTX as well as a data set from like different labs this week. Maybe you want to touch on that a bit. Is it just RT-2 trained on this collective data set, or are there tweaks there?
Yeah. It's just got released, so it's kind of hasn't made it to the slides yet, but yeah, it's basically so we trained both RT1 and RT2 on the data, and actually like both models showed like better performance than like other models that people use, and like single models that people use for their tasks. RT1, I think at some point saturated, so it's like it's getting like bottlenecked because just by the amount of data. So like it seems like RT2 is the way to go there. And yeah, with RT2 we saw some like first signs, like good signs of cross robot transfer. So it is like, I think maybe too early to say that it's like that we can transfer all possible skills across the robot, because we have only like the first evidence that's possible. But yeah, we like could see a good range of new kind of like motions and kind of tasks, new instructions that we couldn't do before. So like, for example, things like put object on top of another object or near another object. So in the RT1 dataset that we used before, we only had move near, so it didn't have move on top. But then in this other robots data sets, there were some tasks where you had to move on top of something. And what we could see is that after training on all of this data, we could actually like execute like move on top, and like which was different from move near on our robot at Google, which basically never saw that like motion before. So that's kind of super encouraging. Like as I mentioned, we are kind of limited by the motion diversity in the RT1 dataset, and we saw that it's like difficult to get out of the motions that are already there. So like yeah, seeing some cross robot of new motions is encouraging. And yeah, of course, I think it's only like there's still a lot of to get out of the data. So it's a huge data set. And I feel like we're really not at the potential what it can do. So I also encourage everyone to like contribute to that data set and also use it. It's like it's really diverse data. The action space is more or less unified, so which is pretty good. So yeah, I think it's quite exciting.
Okay, thanks. I think Liam, you have a question?
Yeah. I mean, first of all, like Yevgen, thank you so much for coming in and telling us about this. And like really like congratulations on this whole line of work. It's like it's incredible, really. Like I think you're really like moving the needle on a lot of things. So like the question that I had is actually kind of like a philosophical question to some degree. So like my sense is that you like the approach that you guys are taking is that you really believe in this like notion of what I would describe as like, Sasha, maybe it's a little bit louder here. Do you want to just like mute while you're off for a second? So that you believe in like what I would call like implicit representations, whereas like what I would argue is like an alternative way that you could have tackled the problems that you're tackling here is with something that's like more explicit in terms of a representation. And that doesn't mean that you can't use vision language models. You would just build an explicit representation of like what these entities are. And then you would perform that query over that explicit representation. And then you would like send whatever the output of that query is to your control algorithm. And then you would execute the control in a way that's like decoupled in some sense from this like reasoning engineering, like you would, another approach would have been to decouple this a little bit more.
Yeah.
And so I'm curious, like, why you feel that this sort of coupled or implicit or whatever, like sort of like vocabulary you want to use is the right way to tackle these problems, or why you guys have decided to go this way. Is there some specific?
Yeah, I think it's actually a great question. In some sense, the decoupled view has been dominating before, right? Because, like in the second work and also RT1, we had let's say a separate language planner and kind of a policy that executes then the commands. Yeah, so first of all, I guess it is an open question what the communication medium is, like would be between these components, right? If we could make it explicit, yes, we can, for example, like communicate through language, right? Like let's say our VLM outputs language, and then we have another model that's conditioned on language again, and kind of now executes low level things. But for me, the problem is that like still these low level components, like if they're not pre-trained on these large data sets, they're like still limited, right? So you still might be bottlenecked by the generation capability of your single component. So the answer to that could be that it's a low level.
Maybe I don't mean to interrupt.
Yeah,
but like so for some of the examples that you show, like and maybe you have to like pick the examples the right way. But like for example, like we're seeing on the screen here is like move the whatever to the 3. Like another model could have parsed the 3 for you. Like like, so I sort of get what you're saying is that like, okay, yes, like somehow coupling these things is maybe like it benefits both. Like I think the like philosophy is that this co-fine tuning approach is beneficial for everybody, right? Like everybody gets better by this like sort of co-fine tuning approach.
Yeah.
But certainly for some of these examples, I don't know, would you agree that like you could also have like fed this image into a VLM thing that asks like where is the number 3, and then like taken the output of that and said like grip this thing and move it to the number 3, and it would have probably worked, like, or not? I don't know. What do you think?
I'm not sure it will be as generalizable, because yeah, the answer, like where, like you just have more points of failure. First of all, like firstly, like your where question can be like it can be basically the prediction might be not good enough, of like localizing objects. I think general object localization, um, it's still a difficult problem on its own. And another thing that, like when you have the single system, right, and then you can just do closed loop control, right? So like meaning that even if it's not good at localizing, just by correcting your arm at all times, you still get there. I think like for me personally, I think I'm attracted to the closed loop nature of it in some sense. So I feel like if you start also decoupling, there's like now you start getting these open loop pieces in some sense, right? So you predict one thing, so now you condition another thing on that thing, and but then you don't update your previous prediction maybe fast enough, or like it's not updated according to the action that the robot thinks it's doing. So there's like this link, the closeness link kind of removed in some sense, which means you might still be able to do it, but you just there could be something that's missing in terms of um, like in terms of those closed loop links. So when you have it in the same model, like you might not need to predict the position of the object. You might just need to make sure that you kind of correct your arm fast enough to kind of do the task. So that makes it it just makes it like it makes it makes it to have more possibilities of to learn the correct things, right? Because you're like not bottlenecked by the communication or by the open loop components. So I think that's one answer to it.
I think I buy that. I mean, I think that makes sense. I mean, like, I think in general, somehow, like, if you have these collective feedback mechanisms, then the hope is that you have a system that's overall more robust. And like, sure, the system that I'm describing, like, maybe it works in this one example, but I buy the like brittleness argument of like, okay, yes, you've had to like do some kind of explicit reasoning and then instruct these like specific things, which if there's any errors in the like chain of reasoning, then you're going to have trouble recovering for them. I have one other question though. I don't know. I want to dominate the discussion, but like, so another sort of like argument that I would make for explicit sort of representations of the world would be that I think, and this is debatable, and I'm curious to hear your perspective, that like, I think that they're arguably probably going to have better scalability properties in terms of scaling to larger environments. And like a lot of what you're showing here is like impressive capabilities, but in relatively like tabletop kind of environments. And so, and I know that, you know, you also had like in RT1, there was the ability for the base to move and stuff, but to what degree do you think this approach that you have in RT2 is going to scale to cases where actually the combination of things that you need in order to do the thing that you're asking the thing to do are like spatially diverse or like far away, or, you know, like they all need to be in memory and representation space at the same time? And is this a limitation, you think, or I don't know what, I'm just curious to get your take.
So good thing that we're dealing with like models that can handle very actually long context lengths at the like, and it's getting more and more, right? So we, you know, things like GPT and also BART, like you can condition them on like thousands of tokens, and they're still working well. So in that sense, I think it might become less of an issue of like splitting things into different models, as all of these different models can be within the same model, right? So like we can just take like this model and just train it to like break down the task into components, or like or do any kind of reasoning and use the same model to then output the action and keep it in the context. So it's like, it seems like it maybe there is not such a big trade-off, as actually what happens, I think, is that you just take all of these kind of components that you thought are actually separate, and you just bring them into the same model. So just, just because you can actually, because it's a general purpose model that can like reason, like that can output whatever you give it, basically, because it's language space. So it's like, it's like hundreds or thousands of tokens it can produce, like different tokens, right? So in that sense, I feel like it's just a matter to figure out like what are the correct kind of training procedures. But in terms of the model itself, I feel like we can just have it all in the same model, because it's like you can literally take all of these kind of single tasks and train the same model to do them, because it's input output space is very generic. So maybe this like the trade-off is not as crucial as we can like have both, basically large single model and some breakdown into steps and kind of reasoning, and and even making things understandable, right? So for example, now you can train the robot to not only like move the arm, but also tell that it moves the arm. Like it can, for example, say I'm moving left, and then move the arm left at the same time. And then in some sense you have the explainability, because you kind of see what it's thinking, and then the actual action. So in some sense it is broken down, but you still have the same model. Yeah, I guess that's would be my kind of intuition here.
Thank you so much. Yeah,
Yeah.
I think that makes sense. Thanks.
Yeah, just a quick follow-up question on this. So right now, my understanding is you only have the current image as well as the language instruction in the input, right?
Yeah.
So in the tabletop setting, I mean, it's related to Liam's question, I guess, but in the tabletop setting, like a single image of your environment has all the information you need to accomplish a task. You see like where the objects are, when you're moving them, you can track them. But yeah, in the context where you need to like go to another room or go to another building even to accomplish a given task, I feel the robot has to have kind of a more, perhaps a more explicit map or a better idea of where it's at. So yeah, how would you tweak the input space of the model to kind of be able to generalize to those tasks?
Yeah. So first of all, it is possible to use image history with these models. Right now it's kind of, from computational perspective, it kind of takes just longer to train and kind of generally requires more compute. But it is possible to use image history. That's what we're like also trying for a lot of things. But yeah, of course, if you have start having very long horizons, you cannot just put all the like images from the last, last 5 or 10 minutes, because it could be too many. So you probably need some kind of like more low-dimensional representation of your history. So I think there are ways to do that. You can always keep, for example, some kind of memory of things you've done, like in language. You can ask to describe it and say, okay, I've been there, and this is the images from the last 10 seconds. So you kind of have like a more abstract history and more like concrete history the closer you get to your current time point. That's one way I can think. But yeah, generally I feel like there are multiple ways to do it. But basically reducing the dimensionality or somehow condensing like the history the further you go back in time. But also there are like some developments now on video models that can actually handle video, and that I think will be very useful here generally for robotics. So that models that can kind of accumulate knowledge in some way of internal representation, given a stream of images, such that you don't have to keep all the images around, but just accumulate it in some internal representation. I think that could be another way to go there, basically.
Awesome. Thanks, Yevgen. Do we have any other questions from the audience? Oh, yes, Sikao.
Okay.
Hi, can you hear me?
I have one.
Yeah.
Should I ask or?
Yeah, go ahead.
Yeah. Thanks a lot for your talk. Sorry, I wasn't there from the beginning. So that's the question I have regarding like having a more motion diversity data set. If we do not do video, is that like how would you do that from like if you do not have
So you mean
on videos, is that possible to have more motion diversity?
yeah, so I think it's a bit difficult to say. I feel like we still need quite a bit of robot data with like action data. So I feel like videos definitely can help in kind of scaling it up and like getting maybe even more diversity. But we need some kind of initial like core, like a good core coverage in the action data. That's my feeling, that like in order to generalize or like to kind of really scale up through the pre-training or through like even if you start using videos, you would need still good amount of robot data to start with. So that I think my current feeling. So I think definitely videos will help a lot with, and we are like not using videos here for pre-training, right? It's just static images from the web. So videos are definitely getting even closer towards the robot experiences. So models that get pre-trained on some like YouTube or something definitely could offer even more transfer possibilities. But at the same time, I think we still need a good chunk of robot data to kind of make sure like it understands actions in the core kind of in its core representation.
Yeah, thanks a lot.
Yeah.
Okay, thank you. I think we had a question from A14. Yeah.
Yes, I have a question which ties back to what you were talking about earlier with these long contexts and like maybe building representations of videos, and I guess in general like this GPT can handle like really long contexts, but it doesn't seem like this is a scalable way to just handle like long histories, and we need to be able to build summarization. Do you think like there's any merit in like I guess going back to RNNs and somehow figuring out how to train them long context, or does the solution seem to just lie in using these transformers to aggregate information, like using these text summarization or something like that?
Yeah. So yeah, it goes. I think this goes into the like kind of more persistent memories, more like things that handle very very long horizons, and I feel there we might not get around like basically information retrieval and things like retro and like that recently people started developing also for large models. So the idea there is usually that you have some kind of a database and your model is able to write and read from it, or like do inference or like search through some keys that are in some embedding space, for example. So yeah, because even if you have 20,000 40,000 tokens in the context, of course it can be always more. Like the lifetime of a robot is like it's millions, so I don't know how many tokens how many tokens a lifetime of a robot could be, but like it's probably not feasible to keep it in the like working memory at all times. So it feels like something like ways where you like actually have some databases of knowledge that you can read and write from dynamically, and kind of do some kind of information retrieval similar to what people now do with things like retro. Feels like that could work there eventually.
Okay. Yeah, thank you. That's it.
All right. Thanks so much for your time, Yevgen. This was a very great talk. So yeah, nice meeting you, and looking forward to your future projects.
Yeah, thanks a lot for inviting, and great discussion. I really enjoyed it. Thank you.
Awesome.
Thanks so much. This is really great. Yeah.
Thank you.
Yeah.
Okay.
Thank you. Goodbye,
Bye-bye.
everyone.
Bye.